First event, Dynamic Planet Oceanography. I've already said this is my favorite event. And yeah, so basically, kind of straightforward. This is going to be all about oceanography, all about the ocean, a bit about like kind of like I guess the physics behind it, a bit of the biology behind it. So yeah. So basically, this is kind of how the events have gone rotated in the past. We've had oceanography. I think we've also had hydrology, and then now we're back to earthquakes, volcanoes, and tectonics. I think these two have been kind of combined. But yeah, um, this is basically, yeah, event rotation. Seems like oceanography might return sometime soon in a few seasons or so. So, I feel like this information could be useful for people maybe down the line if they want to continue with Siley. Right. Let's get into the
Um, Wait,
yes,
do you know why it doesn't have 2023 on there?
because this is outdated slides. Uh,
Okay.
yeah, I think after that was another season of hydrology, and then we moved on to earthquakes, volcanoes, and tectonics. Anyways, let's move on to the content. So I feel like it's natural when we're talking about oceanography to start with seawater. And the first thing, I'll start to mention by saying that seawater is 3.5% salt, and that's 35 parts per thousand. This is a fact that gets tested a lot, and I feel like it's a relatively simple number to memorize, so don't freak out. The salinity of water is the highest actually at the mid latitudes, and this is actually quite interesting. Reason being is that at the poles, there isn't going to be a lot of evaporation. So there's going to be a lot of water that can kind of hold all the salt content. And at the equator, there's a lot of rain. Precipitation is the formal word. But this will also add water. And so the concentration of salts compared to water is going to be less. Therefore, at the mid latitudes, where these two are kind of in balance, then this is where the salinity is highest. Also note that the melting point of seawater is actually not 0 Celsius. It's not 32 Fahrenheit. It's actually a bit less because the salts can help the water molecules kind of stay closer to each other. And it kind of no, is that the right explanation? Yeah, no, but the salts kind of gets in the way of the water kind of like forming ice, and so the melting point is a bit less. No, this is just seawater. Normal water is still 0 Celsius, but seawater is not normal water. Seawater is water with personality. Where are the mid latitudes? I'd say they're between 30 and 60 latitude. Thought chlorine was dangerous. That is chlorine gas, so that's Cl2. But in its ionic form, like Cl minus, it's actually quite harmless. Like there's that meme that circulates all the time where it's like sodium is really explosive. Fun fact, you throw sodium onto water and it blows the hell up. Chlorine, super dangerous, used as a chemical weapon in World War One. And then you combine them together and then you get table salt, which is a really harmless compound. So yeah. Does salt interfere with the melting points and bonding molecules? Yeah. I think yeah, that is generally how it's explained. Right, moving on because we have a ton of stuff to get to, and I think we might not get through all of it. Okay, let's talk about how water interacts with heat a bit more. So, this applies to all water, but some of you might have heard the term of like a high like heat capacity. So, water has a really high heat capacity, meaning that it's able to, or that means it's kind of hard to heat up water. Like these are the numbers that for like certain substances. Like for metals, you might know like if you leave metals out in the sun, they can get really hot. Not water. Water kind of acts like a temperature mediator. And so that's why, for example, like your body has a lot of water, so you don't like overheat in this when you like step out into the sun. And it's also why you don't like literally freeze over when like in the winter. So we really have water to thank for that. Um, so yeah, that's heat capacity. And also it has a high like latent heat of fusion and vaporization, which basically just means that it's really hard to like evaporate water. It's hard to get water to change states. So yeah. This you'll talk about a bit more in like a chemistry class, but yeah. So what does this mean for the oceans? Well, this means that like the oceans kind of mediate temperatures. So like for example, I live in the Bay Area. I'm like a 30-minute drive from the ocean. And so basically temperatures here are really mild. Like we basically never go below 50 Fahrenheit and we never really go above like 90, 95. So yeah. Also it never snows here. So am I missing out? Probably. But yeah, that's kind of how the oceans can kind of change can kind of change the weather. So yeah. All right. Well, let's actually go into the ocean and talk a bit more about some divisions within the ocean. So let's first talk about what I refers to latent. Okay, first question. Latent heat is the amount of energy needed to change states. Yes, I think that should be right. Yes. Okay. Zones of the ocean. So let's first talk about what I call the three clines. So basically, the these clines are just areas where some specific property of the ocean drops very rapidly. For example, this is the thermocline, which basically a bit past 500 meters deep in the ocean, we actually see that the temperature of the water drops really steeply from your like standard temperatures, your standard atmospheric temperature, all the way down to like single digits Celsius, around 4 degrees Celsius. And the reason for this is that this is about the level to where sunlight can kind of penetrate. And I'm actually just going to transition over to this diagram for a sec. This kind of corresponds to like the photic zone here, where this is like the area where there's a lot of light that gets received by the sun. If you know phytoplankton, you're gonna see a lot of them hanging out here. But like deeper down, then because you don't have like sunlight to warm up, now the water can go really, really, really cold. So yeah. Uh, So yeah, the thermocline isn't the only cline though. There's also the halocline and the lysocline. Basically, the halocline you can use kind of word prefixes to kind of engineer what these clines are. Halo means salt, so the halocline is a region where like the salinity of the ocean, I think, actually rises considerably, and the lysocline has to do with the cal concentration of calcium carbonate. These are all kind of important, and these have all been tested a bit. Okay, moving on to this five-layer destruction of the ocean. Um, this is very detailed diagram, and I forgot to say in our introduction, but I really do think like a picture is worth 1,000 words. I really think that holds true. And for example, like this holds so much more information that we can't just replicate with just words. Um, Oh, I am being distracted by a good question. How can creatures get oxygen towards the bottom layers? So I think oxygen is dissolved within the water. And so yeah, because I don't think there's like an oxygen a client for the oxygen. And so I think because of that, then a lot of the organisms are able to still be able to take in oxygen even from in the deep layers of the ocean. Yeah, please don't like spam GIFs and whatever. We have enough of that going on. Um, it's very cold and pressured. What do you mean by that? I guess the water is, but I guess yeah. Does ocean warming affect the temperatures in the deeper regions of the ocean? That's a good question. I think global warming isn't powerful enough yet to raise the temperatures at the really bottom. But then again, the temperatures, it is usually the top kilometer of the ocean that has a lot of like wildlife, or it's kind of like the marine life. And so like coral reefs and stuff, they're within the top 1,000. They're heavily affected by global warming. Like the temperature here, like I'm just gonna just draw this here. can I draw? Yeah, instead of the thermocline looking like this, like you might get a thermocline that looks a bit more like this, where there's going to be significant change up here and then a bit less up here, but this is like what we care about. So yeah. Bottom line, global warming bad. This will be a recurring theme, maybe, I think. Yeah. So yeah, I still have not talked about the five zones of the ocean. Here they are. I think these have different names, like you can call them like the pelagic zones. I think there are other names for these. I don't even think you need the pelagic behind it. But yeah, these are just other ways to divide the ocean that they might sometimes test you about. The abyss. That is true. The abyss. Next. Okay. Ocean topography. You might think that the bottom of the ocean is just one big flat plane. And while abyssal plains do exist, we actually see that the bottom of the ocean can be a lot more interesting than what might appear to meet the eye. For example, okay, we obviously can have content over here, but then sometimes it might fall off into the computational shelf. And so this is basically like a period, like I think this is one of the zones covered previously, but basically over here, the depth of the ocean goes from like 10-ish or so meters all the way down to a few, I think, kilometers deep. And then, so yeah, continental shelf a few meters deep, continental slope really deep. You might also have like volcanic islands where you probably heard of this before, volcanoes in the middle of the ocean spew out rock. Eventually, they can um, grow taller, and then they can reach the surface of the ocean. Is this to scale? No. Yeah. What are the cause and effects for these topographical features? Geez, you are asking really good questions today. Um, let's see. Most of these are just, I think, caused by tectonics and whatever. Like, for example, you like oceanic trenches, you can find them a lot at fault lines. The volcanic islands are obviously caused by volcanoes. Mid-ocean ridges, which is what I'm going to talk about a bit more in depth. I think these are also like caused by these tectonics also have a big say in. Okay. Speaking of mid-ocean ridges, how many people here have heard of like the Mid-Atlantic Ridge, for example? Yep. It seems like some people have. Um, okay. In the meantime, we have a question. How long does it take for lava in the water to cool down? Basically instantaneously. Like, I don't know if you've seen videos of, okay, very fun fact, very off topic too. If you've ever watched a video of people like collecting fresh rock, which doesn't seem like it makes sense, but hear me out. You basically have lava like that's flowing out really slowly from a volcano, and there's gonna be people who have like these scoops and they're just gonna like scoop lava into a bucket and then like almost instantly forms rock. And then it just instantly cools down to form rocks. And then like based on that, you can like infer a few things about the volcanoes, like the age and then whatever. And yeah, so that's kind of cool. And Helen is correct. Conservation of energy. If you have water cooling the rock, then you have the rock heating the water, and then yeah, uh, the water heats up. How long exactly? I think it's too short for you to really like care about. Yeah, especially when we're talking about processes that can happen over like millions of years. It basically this basically happens in a flash. Minecraft reference is funny, I guess, maybe. Okay, we have been off topic. It's been 15 minutes already. Okay, this is bad. Okay, we have to hurry up. We have to hurry up. Okay, you have a mid-ocean ridge. Basically what happens here is that rock from the bottom is going to like move up into this mid-ocean ridge and it's going to spread to the side. So the movement of the rock would look something more like this. And this is really interesting because like all the rock here is going to be newer, and then so if you check the age of rocks in the ocean, you're going to see the older rocks are towards the continents, while newer rocks are formed in the center. And one of the cool pieces of evidence for continental drift that I learned in middle school, it was that if you look at the rocks near like South America, they're relatively Yeah, no, they are relatively new rocks, which suggests that South America has like moved over into a mid-ocean, oh, what used to be mid-ocean ridge. That's kind of cool. Um, Seamounts are mountains that are not volcanic islands, but they're just mountains in the sea. Guyats are seamounts with a flat top. I think this is caused by currents. You have your obvious abyssal plain, and you have some trenches that go deep into the ocean, like the Mariana Trench, which is a very trenchy trench. Okay, let's talk a bit more about tectonics. So basically, when you have an oceanic crust meeting continental crust, the oceanic crust is going to go down because it's denser. Like for example, if you like think about anything that sinks anything sinks because it's denser than water. And so this actually kind of happens for solids as well. The oceanic crust is going to sink below the continental crust. And then so obviously because if you have crust that's moving this way, you're going to leave an opening in the middle, and that's where kind of the mid-ocean ridges come into play. This I forgot, but mid-ocean ridges lead to like seafloor spreading. So basically, like I was talking kind of about, excuse me, how rocks kind of move off to the side. That's a process known as seafloor spreading. And then so this exposes new rock at the middle. And actually, this is a really, really, really fun fact. If you want to a bit more of a you want a bit more of an explanation, I can talk about why. But this actually forms areas of reverse magnetic polarity. And one of the fun facts is that they were able to use this to kind of determine that the magnetic field of the Earth kind of shifts around. So like you might have heard like magnetic field like flipping sometimes. Yeah, it is one of the reasons. This is one of the pieces of evidence that scientists use to determine that. Okay. Now let's move on to coral reefs because this is also very important and this is actually very cool. You might have heard of a guy called Charles Darwin. Who here knows what Charles Darwin is most famous for?
Human evolution?
Not just of humans, evolution of everything, survival of the fittest. Yeah, I see a lot of people in the chat. Lauren, are you just raising your hand to say that you know, or do you have a question? Lauren? Okay, moving on. Yeah, Darwin, you might have heard him because he did his whole spiel on evolution, but he also had a bit of a theory onto how atolls form. And so, yeah, this you need to know. This is actually very cool. So first, in the first step of forming an atoll, you have an active volcano, and then after a while, for some reason, oh, the audio won't work. You can type it in chat if you want. Um, if you have an active volcano, for some reason, it becomes dormant, so it's no longer like growing itself. And so the first step that happens is one of the four reef types. A fringing reef is going to form around the volcano, like just off the coast of the volcano. And then as the volcano kind of sinks, you're going to form like barrier reef. So for example, like think Great Barrier Reef of Australia. And finally when the volcano sinks below the surface, you get an atoll. And so that is three of the four types of reefs. I think the final type of reef is called a patch reef. It's just I think it's kind of it's like your miscellaneous box of a reef type. Like if you can't classify into one of these three, you just throw it into patch reef and then worry about it sometime else, I guess. Yeah. What Helen's saying in the chat is also absolutely correct. Okay, let's talk about waves because they're probably what you think about when we talk about ocean first. Okay, we classify waves into two types based on their depth. And annoyingly, this leaves rooms for a third type of wave that we don't really care about. So we classify, oh dear, it's storming right now. Come back next time for meteorology, where we'll talk a lot about storms. Sorry, I had to do that plug. But yeah, like all the time. Yeah, especially in summer, but this is Dynamic Planet. Samuel and I did Dynamic Planet and Meteorology. So we made the executive decision to split me to do Dynamic Planet, and you'll see him in Meteorology. So yeah, he's a good teacher for sure. So Yeah, you'll learn a lot from him. What's the worst event? Don't tell anyone, but I think it's anatomy. I really didn't like that event, even though I did it. Yeah, I don't like it. Okay. Get back on track. Deep water waves are classified when their depth is greater than lambda over 2. And this just means then lambda just refers to the wavelength. If any of you have taken like physics of waves, then this is kind of standard notation. So when the depth is greater than lambda over 2, that's when you have a deep water wave. And then when depth is less than lambda over 20, that's when you get a shallow water wave. No, I'm pretty sure this isn't a typo. They really just did this. Yeah, there was really bad tsunami in Japan, Fuga 2011, and yeah. Ooh, okay. I'm gonna give you all a spoiler. There's gonna be a question on wave speeds in the Kahoot, and this is gonna be kind of important. So maybe you want to listen up. I don't know. What if it's greater than over 20 and smaller than over 2? Yeah, that's what I was talking about of like the gray zone of we don't care what type of wave this is. I'm not aware of a classification for those types of waves. Yeah. The funky symbol I explained, it's lambda. Basically, it represents the wavelength. So yeah. Anyways, the different types of tsunamis. No, there tsunamis, I think generally they're formed all the same way. Usually it's some really big disturbance in the middle of the ocean, and then that disturbance kind of moves towards land. I guess in the example of like Fukushima, that the disturbance was rather close to Japan, but then like the tsunami just spread out across the Pacific and then ended up in California later. Um, yeah. All tsunamis are shallow water waves because their depths, because their wavelengths, I think. Is it? Yeah, no, yeah, because their wavelengths are just way too big. Um, yeah. Anything else I'm missing? No, I guess rogue waves too. Rogue waves, they're 2 times taller than the surrounding waves. Usually they'll find them in like the middle of the ocean, but they're more just kind of, and this is just more of an off-the-side isolated fact. And yeah, a bit more about basic wave physics if you guys need to like I guess bit of a refresher on waves. Uh, let's see. Yeah, we can talk a bit more about the earthquake in a sec, but let's continue talking about waves right now. So yeah, the general formula for the speed, if you've taken any physics at all, you're going to learn that velocity is like distance over time. And basically, this is kind of the same concept. The lambda is the wavelength over time, just says, okay, how far is the wave traveling in 1 unit of time? Um, the frequency is just 1 over the time, and so you memorize this. The speed of shallow water waves is this v equals the square root of gd, where g is gravitational acceleration, 9.1 meters per second squared. Is F equals 8 hertz? That is right. Yeah, this is a funny formula that I am frankly not sure where they got this from, but it's kind of cool. Okay. Movement of water molecules in the open ocean. This is a really common misconception, or I think, or at least I've been told it's a really common misconception among physics students. And because waves are a type of wave, we're going to talk about this too. So waves transport energy, not matter. And so it's important to know, like, for example, like just because there's waves going onto like a beach, the beach isn't like gaining water and the ocean's losing water. No. Um, Water is staying relatively stable in its location over time. And the only reason why it would move is due to currents, which we'll talk about a bit more later. Joy,
Wait,
go.
but if the wave is like carrying like rocks and like shells and like stones, does it count as carrying matter or?
Well, okay, this is kind of confusing. But like when we're talking about a wave, we're talking about like what forms the wave. So like
Oh,
the
okay.
medium through which the waves pass through the water, nothing changes about that. Rocks and the other stuff might get pushed by waves wherever. What type of wave is water? Okay. Okay. Generally, it's easier to think about them as transverse waves, but actually, I think it's actually not. I don't think it's actually accurate to classify them as transverse waves. To my knowledge, they're actually a special type of wave called a Rayleigh wave, which is kind of similar to a transverse wave, but it's a bit different. But I think for all intents and purposes, we can say it's a transverse wave. All right, I'll give you what I think is the spelling for it. You can search this up to test if I am a really big idiot, but um, yeah, this might be. I feel like this is right. Okay, what does F, T, and D stand for? F is the frequency, and T is the time. So basically, like this is just a unit time that you will arbitrarily choose. D is the depth, and G is gravitational acceleration, 9.81 meters per second squared. Okay. Yeah. So instead of water molecules moving, it's also in like no, not really scattering, Rayleigh waves. Rayleigh scattering is something else. Yeah. Okay. G is gravitational acceleration, not the force. So like, oh, this I'm gonna go on such a big physics tangent. Do we have time for this? Oh, we have time for everything. Okay. Um, so gravity exerts a force on everything, and then so like but for some reason, the acceleration of all objects by the Earth is the same. So, like how fast an object is pulled by an Earth, that never changes. So that is a constant value for everything. And then so we multiply that by the depth of the water, and then we square root that, and then we get the speed. Somehow it works out. I don't know why. I'm not good enough in physics to know that. Jeremy, please stop spamming for God. Okay. Yeah, so instead of not moving at all, actually, water molecules tend to move in a circular pattern. So that's kind of interesting, kind of fun fact. Okay. Uh, okay, let's just speed through the rest of this. Wave associated phenomena. I think I have images for this in the next slide, so it's probably easy to know. Why does it move in a circle? I think, like, if you visualize it, I think it might be easier. I'm not exactly sure why it moves in a circle. What time does class end? It's supposed to end, I guess for your time, it's gonna be supposed to end 7:30. I have like literally 2 minutes to cover the rest of the stuff, which is impossible, but I will do my best. Or we might need to go a bit over time for the Kahoots. Sorry about that. Okay. Anyways, Jesus Christ. Okay. We have fetch, swell, and surf. First of all is fetch, and this is basically where this is just basically the area over where a wind blows and forms waves. Basically, every single wave you're gonna find in the ocean is caused by the wind, with the rare exceptions being like tsunamis and stuff that are from earthquakes. And so the fetch is the area over this. The swell is like the surface of like surface gravity waves that travel together. So like for example, in this middle image, we see like kind of like a row of waves kind of coming onto. I don't know if this is a shore now. This seems like a shore, and yeah, the surf of a wave is kind of when it's like breaking. It's like this middle section where you do surfing on. So that's really easy to memorize. And yeah, these are just I think these are more of the isolated facts. So I'm gonna like brush over them a bit quicker for the more like more like tied together concepts. I'm gonna spend a bit more time on. Okay. Now let's talk about waves breaking because that's the interesting part of waves. Do we just have waves like going on forever? That would be kind of boring, but imagine if we had waves, imagine if we had waves breaking. Now we're talking. Okay. There are three types of waves breaking, and these are all determined by basically the slope at which the beach is. So, for example, if you have a spilling breaker, you have a really flat beach, and this is just going to be small spills. If you have like a steeper beach, you have plunging, then you have very steep, you're going to have surging. Basically, a bit more of the description is over here. Fun fact, the West Coast has far larger waves than the East. Why? I'm not even sure. This is also just another kind of isolated fact. Um, okay, let's talk about why waves break in the first place. So basically, let's imagine like for example, okay. Let me draw because I'm a really good artist. I want to flex my drawing skills. Okay. Let's say you have a bunch of water molecules that are stacked on top of each other here. So in like the open ocean, these can be stacked like quite a bit, right? So like over here, I have like 6 molecules at the surface. But over here, if I want to draw 6 molecules, they have to be kind of flattened and eventually like look, okay, my drawing skills are so poor that I can't even fit six of them. Um, Eventually gravity is going to like pull on like the top parts of the wave, and then eventually the wave kind of collapses on itself. And then that's when it starts to break, and then eventually the whole wave breaks. You crash onto the side of the beach, and then that's that. Um, right, that's it for wave breaking, I think. Okay, currents. Finally, we're on currents. Okay. Um, Coastal currents. There are three types, depending on kind of like where on the coast you are. First is a longshore current, and this is basically a current that kind of hits the shore at an angle. So let's say we have a really cool beach over here. A longshore current, for example, would kind of hit the beach. What's a good color to use this way? Towards the side. And then this is kind of responsible for bringing like sand and stuff over here up towards this side of the beach, for example. And so that's kind of how longshore currents operate. Rip currents operates a bit differently. You might have heard them as rip tides, and they've been known to be a bit of a danger if you're swimming. The reason being that these are waves that like these are currents that move away from the shore. And so basically, if you're Mr. Swimmer over here, you're gonna get caught up over here. And if you try to fight it, please do not try to fight it because you are not going to be stronger than the rip tide. Instead, what you should do to survive pro life hacks with Andrew in Siley Camp. If you're stuck in a
Swim
riptide,
to the side.
yeah, when you're in a rip current, swim to the side. Basically, you're not going to be impeded that way, and then maybe you can escape the rip current. Normally, they're rather thin, so like you're not going to have to swim very far to escape from the current. You might be like carried a bit further away from shore, but it's better than wasting all your energy and then not having enough energy to come back to the shore. Yeah. Finally, there's upwelling, which happens in kind of the third dimension. So if we can kind of like imagine like this is like the coast and like this is the and like this is like this surface level of the seawater, then upwelling basically happens when you have like water from the very deep, does a bit of a flip turn, and it moves to the surface. This is incredibly important because colder water is generally associated with being more nutritious. And so, for example, like okay, yeah, I'm answering this question right now, actually. Upwelling water is and cold water has really high, it's probably high in nutrients, and so upwelling will bring all these cold nutrients in the bottom of the ocean towards the top, and so this kind of just cycles nutrients stored through an ecosystem. I'm going to talk about this a bit more when I get into El Nino, but basically in El Nino, upwelling along this coast of Peru stops, and so that's really bad for fishermen there because all the nutrients they're given to the fishies could take is going to die. Why is cold water high in nutrients? Um, I think this just has to do with like the purity of water and like the lack of contaminants, and also like the fact that there's going to be a lot of organisms near to the warm water that are using up all the nutrients. All the Minecraft references are going so hard in this class today. Anyways. Okay, oceanic circulation. Imagine if currents were really big. So this over here, I talked about this a bit before, but these are the five major gyres. North-South Pacific, North-South Atlantic, and Indian Ocean. Basically, these are kind of circles in which water rotates. The reasons why they rotate counterclockwise, yeah, no, this is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere has to do with this thing called the Coriolis effect that you guys can search up a bit more because I do not have time to talk about it. Anyway, what the hell happened? Okay. Anyways, so yeah, remember it's like heat and density. This is actually called thermohaline circulation, which no, thermohaline circulation is something else. Sorry. Yeah, so five gyres. Okay, I'm going to talk a bit about Western intensification because spoiler, there's going to be a Kahoot question on this. But basically, the currents in the west of the gyre are generally going to be like narrower and quicker. And so, for example, like the currents like on the side of Japan, these are going to be narrower and quicker because okay. It's kind of hard to talk about this without explaining the Coriolis effect. I don't think I have time to explain the Coriolis effect. Okay, if you want me to explain more about this, you can say after class and then we can do it. All right. Tides repeat every 24 hours. Wrong. 24 it's every 24 hours and 50 minutes. That's kind of important. This is a really easy place to trip up This is a really easy place to trip up and for them to like, yeah. Where these currents are used for trade? Well, those are different currents, I think. And usually you use like wind patterns if you want to do trades earlier, but yeah. If you want to do you did trading in earlier history, but I'm getting off track again. Basically, there's three types of like tide patterns. You can have diurnal where you just do a one high and one low within this 24 hours or 50 minutes. You have semi-diurnal where you have two highs and two lows, and you have mixed, which is where you have two high tides of different heights and two low tides of different heights. So this is actually really interesting, and it's a good idea actually kind of to know like if you live like along the coast where like what types of tides you have. For example, like I live near San Francisco, so we actually have mixed tides here. That's something interesting to talk about. Um, Tides are caused by the moon. Wrong, they're also caused by the sun. Basically, in this diagram over here, I'm basically showing spring tides and neap tides. So basically, spring tides are where the moon and the sun are kind of aligned together, and so they can pull on the tides together. Whereas neap tides, the moon and the sun pull opposite, and so yeah. And yes, the sun does have a smaller effect on the moon because it's so far away. And so the moon will ha always has a greater one, but it just depends on whether the effects add up or cancel out. Okay. Also, the highest tides are in the Bay of Fundy. As I was saying, the Minecraft references in this class are going to be real. There's going to be a lot of them. Okay. Finally, we're on El Nino. Okay. Um, El Nino is basically technically it's called the El Nino Southern Oscillation. Uh, this is how it's measured. Basically, El Nino happens when you have this reverse equatorial countercurrent. So I'm talking about like normally there's upwelling here, but then actually in El Nino, the current here reverses, and so there's actually downwelling here, and this causes, like as I've said, like a lack of nutrients within Peru, and so there's a bunch of effects around where precipitation gets more, where it gets less, and so yeah, that's yeah, that's kind of I'm blinking, sorry. Yeah, so you should all memorize that. I don't have time to talk about it right now. Tools for oceanic research. You should know a few of these. I'm just talk about a few right now. You have a Nansen bottle, which can sample water from the ocean. You can also have dredges, which can kind of like analyze the contents of the seafloor. But I will say the dredge generally, yeah, its use is questionable since you might be damaging the seafloor. Okay. Tips and tricks. Dynamic Planet is a binder event, so you basically have infinite room to write everything down. So please don't be concerned about saving space, but do be readable and do follow like the events guidelines. But other than that, yeah, binder events I think are overpowered, and I think one of the reasons why I love Dynamic Planet so much is because they have a full binder. I don't have time to go back. If you want to stay after class, you can do it. Jesus Christ. Okay. That's it from the presentation. If you guys want to do the Kahoot, we can do it right now. Joy, I think you had a question.
Do you have to do the Kahoot or can you like go right now?
If you want to go, I suppose you can go. All right.
But
When an
but
atoll is being created, why does the volcano sink?
Um,
Tectonics?
okay. Okay. Volcano is always like trying to either is a volcano like always tries to build itself through like sorry, I'm busy getting the coop set up. Here's a link. I'll answer the question in the meantime. So, um yeah, the volcano always tries to build itself by like spitting out new rock, right? But at the same time, what the water, also the ocean water is also kind of trying to like attack the volcano, and for whatever reasons, the rock might be getting eroded and whatever. And the reason why the volcano is sinking, this is just when like the volcano has like stopped adding new rock to itself, and so like basically it's no longer building itself up, and so it's only being subjected to forces that wear it down. So that's why it sinks.
Also, where's the Kahoot link?
Just go to kahoot.it and then enter this pin.
Oh yeah, if you're wondering, I'm Chunky D Monkey.
Cool. Uh, let's see. When people stop joining, I will start it.
Chunky D Monkey.
Okay, Elaine, where did you want me to talk a bit more about? The important part to know about from the ENSO page, it's just I was talking about the equatorial countercurrents and like how water flow in the ocean is kind of
Doesn't work. It doesn't work.
no, why doesn't it work?
The ID doesn't work.
Not this pin doesn't work.
H
Just
three seven
just type in the thing without the space.
I know, I did, and it doesn't work.
Then try it again.
I'm sorry, I really don't know what's going on, and I don't think I can help that well. Okay, it seems like people are stopping or not joining anymore, so let me start it. Da-da-da.
Click.
This one, I guess you can kind of derive it. Oh, I didn't actually mention this one. It's between, there's two obviously right choices and two obviously wrong choices, but I think there's going to be more chlorine inside the ocean. Sorry for everyone who guessed sodium, but Cl is the top at 55%. I think sodium is closer to 30%. Or I don't know if it's not percent. It might be some other metric. This I talked about a bit. All right. Seems like most of you remembered that a Escura is just a seamount with a flat top. This is just something to memorize. Let's go quickly. Okay, this is the wave speed one I was talking about. I'll give hints at 20 seconds and 40 seconds. You have a minute to do this. Well, I'm not going to give it 20 seconds right now. I'm just going to give you the hints right now. All right, never mind. That's not the right sentence. Okay. The answer is 13 hours. I think using the wave formulas, you can cook up some calculation that will get this. Um, I think you have to, I think you can actually just multiply the lambda and the frequency to get like the speed of the wave and then do a bit of division to get the and then just get the time it takes to get there. So yeah. My voice is so dead. Which of the current is faster? Okay. In case you guys are not the best at geography, I'll label them. The answer A is about here. B, C, D. Okay. Nice. Looks like most of you who answered got this one. This is just Western intensification. The Kuroshio current is on the sorry, western side of the North Pacific Gyre. And actually, the Kuroshio current is the fastest current in the world, so that might be tested. Kind of fun. Hmm. Next. Okay. This is about tides. Remember when I said something about testing the timing of
Shoot,
time?
I got it wrong. If I was
Well,
24 hours instead of 24 hours, 50 minutes.
yeah, that's the trap that's set. Oh dear.
I'm still in fifth place.
Mixed.
one got it right.
That's yeah. Mixed tide. Okay, I should review this a bit more then.
Very concerned.
Mixed tides refer to when you have two high tides and two low tides. If we like kind of recall the diagram,
Hi.
it would look something like high, high, low, 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 high, high, low, and then back again. And so, for example, like John, if our hypothetical John sees a high tide at 7 a.m., um, the next high tide will be 12 hours and 25 minutes later on the same day. So that would be 7:25 p.m. Okay. Hopefully this is clear to everyone. Next question. I talked a bit about this one too. All right, good. Most of you got this right. It is a longshore current. Longshore currents can move things along coasts. Next question. This is a labeling diagram.
I'm unmuted now.
Talk about this, but I feel like I talked about the rest of the other three, and it's not the rest of the other three. So, yep. Any of you who live near the Bay Area, one of these is near Monterey, which is kind of interesting. Okay, yeah. That was a submarine canyon. I didn't really talk about this in detail, but um, a trench. The rest of these three normally would form in the abyssal plain, and so that's why they're not. And that is why they can't be.
Again.
Yeah. Well, I didn't. Oh shoot! I forgot to talk about pH. Salt water has a pH of 8.1. This is a very important fact that I completely missed. But pure water, for context, has a pH of 7. So I gave you half of the problem. I talked about the other half of the problem during the lesson. And yeah, seawater has a lower freezing point and a higher pH. And the other people, most of you all chose a lower freezing point. I'm sorry, I completely forgot to talk about pH. But yeah. Okay, this is a bit about the equatorial countercurrent thing. Um, Normally the current runs this way, but also right now because the ocean current is warmer and
Mena.
that way, um, I believe yeah, we're going to just be in El Nino. La Nina would be kind of the opposite, where the surface temperatures are cooler and there's a very strong there's very strong upwelling. So yeah. Last question. Okay, this is kind of a looking back on this question that I wrote years ago, it's not the best, but I did talk about all of these, I think. All right, nice. Still seems like a lot of you got this one correctly. This would actually be have the youngest rocks in the middle, so you'd have an increase in a rock age the further away from the middle you are. So if you are spreading, I mean, oh yeah, fun fact, the Atlantic is increasing in size, and the Pacific is decreasing in size. Partially, the Mid-Atlantic range is to blame. New rock is associated with mid-ocean ridges. This is true. And the magnetic reversals is that kind of fun fact that I was talking about from earlier. All right, let's see who won. Chunk the Monkey.
That's me. Chunky
Nice.
D Monkey is me. Period. Also known as Javon.
And 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, good job, everyone. And yeah, this concludes the first day of study camp.